Your control room flatlines, then spikes without warning on August 18, 2025. Detectors across the United States and Italy register a violent ripple tearing through space-time itself. Every instrument in the room agrees within seconds. Two neutron stars have collided in a distant galaxy, producing the exact signature astronomers have hunted since 2017. The explosion astronomers detected in August 2025 looked exactly like two dead stars colliding, until days later it began behaving like something else entirely, and the truth hiding inside it may rewrite how stars die. Telescopes swing toward those coordinates within hours. Confidence fills the room like a held breath finally released. Gravitational wave detectors handed astronomers a precise location within minutes of the event. Optical telescopes across multiple continents lock onto that exact patch of sky. Every early measurement matches the textbook signature of a kilonova perfectly. Light glows briefly, fades on schedule, and behaves exactly as merger models predict. 3 days pass with data confirming the same clean, familiar story. Certainty collapses on day 4. Light curves for genuine kilonova always fade steadily after their initial peak. This light curve does something no kilonova should ever do. Brightness climbs a second time, catching every observing team off guard. Color shifts bluer, a change merger debris rarely produces this late. Hydrogen lines emerge in the spectrum, a signature completely foreign to colliding neutron stars. Astronomers scramble to explain a pattern their models never predicted for this type of event. Your screen shows two death signatures fighting for the same explosion. Scientific training teaches researchers to trust a confirmed classification once clear evidence locks it in. Consistent signals typically point toward one consistent physical cause across the entire observing window. That trained instinct meets a direct contradiction inside this single object, cataloged as AT-2025-OUZ. Merger signatures dominate the first 3 days of observation with total clarity. Supernova signatures then emerge and dominate the data that follows immediately after. Both signatures belong to fundamentally different ways for a star to die. Neutron star mergers require two dense, ancient stellar corpses drifting toward each other for eons. Core collapse supernovae instead require one massive, actively fusing star running out of fuel. AT-2025-OUZ presents convincing evidence for both scenarios within the exact same explosion. Trusting the first signal nearly buried the far stranger reality hiding directly underneath it. Investigators first walked through every conventional explanation available to them. Instrument malfunction seemed like the simplest possible answer during those first confusing hours. Engineers checked calibration logs across every telescope reporting the unusual secondary brightening. Every instrument passed its diagnostic checks, ruling out equipment failure as a straightforward culprit. Background contamination from an unrelated foreground object became the next candidate under review. Careful positional analysis confirmed the brightening originated from the exact same coordinates as the original merger. Each ruled-out explanation pushed researchers closer toward accepting a genuinely novel physical process. Spectral analysis delivered the clearest evidence separating this event from any known kilonova. Kilonovas typically show heavy element signatures, produced when neutron-rich material slams together and fuses instantly. Elements like gold, platinum, and other rare heavy metals leave distinct fingerprints across the light spectrum. AT-2025-ULZ showed those exact heavy element fingerprints during its first 3 days of observation. Hydrogen signatures then abruptly appeared, a chemical fingerprint completely absent from genuine neutron star mergers. Hydrogen belongs to massive, actively fusing stars shedding their outer layers, not ancient collapsed remnants. Finding both fingerprints stacked inside one event demanded an explanation spanning two entirely different stellar death mechanisms. Timing between these two signatures carries enormous scientific weight. Traditional supernovae take weeks or months to reach their peak brightness after collapse begins. Traditional kilonovae instead peak and fade within days, moving far faster than typical supernova light curves. AT 2025 ULZ compressed both timelines into a single, tightly overlapping sequence lasting roughly a week. Compression this tight only makes physical sense if both explosions originated from nearly the same collapsing core. Separate, unrelated events occurring by pure coincidence would almost certainly show a wider timing gap between them. The buried reality begins deep inside a single dying star, not two. A massive, rapidly spinning star exhausts its nuclear fuel reserves completely. Its core collapses under crushing gravity within a fraction of a second. Rotation this fast changes the outcome of that collapse dramatically. Instead of forming one stable neutron star, the collapsing core splits or reforms into two. Both objects emerge simultaneously, born at a devastatingly close orbital distance from each other. Two neutron stars locked at that distance cannot remain separate for long. Gravity pulls the newborn pair toward each other within hours, not eons. Extreme proximity forces a merger far faster than any ordinary neutron-star binary experiences. That merger triggers a smaller, secondary detonation, a genuine kilonova. Light from that kilonova briefly escapes into space, carrying the true signature of a stellar merger. A slower, brighter wave of supernova debris then expands outward behind it, swallowing that early light. The kilonova's signature buries itself inside layers of hot, glowing debris rather than vanishing outright. You picture two explosions stacked directly on top of each other in time. Sequence matters enormously here, reshaping the entire mystery into something coherent. Supernova light dominates first because it originates from the outer layers exploding outward immediately. Kilonova light escapes early too, but weaker, fainter, easily lost inside the brighter blast surrounding it. Days later, the supernova's initial glow thins as debris expands and cools. Brightening returns as the kilonova's hidden light finally pushes back through. Astronomers watched one buried signature slowly reveal itself through thinning debris, not a second explosion joining the first. Rotation speed inside the original star explains why this rare split occurred at all. Most collapsing stellar cores spin slowly enough to settle into one single stable neutron star. Extremely fast rotation instead distributes angular momentum unevenly throughout the collapsing material. Uneven distribution creates conditions favorable for the core to fragment into two separate objects. Only a small fraction of massive stars spin fast enough to trigger this rare outcome. Rarity like this explains why confirmed examples remained purely theoretical for over a decade. Astronomers needed a star spinning within a narrow, specific rotational range to produce this exact sequence. Spin too slowly, and the core simply collapses into one ordinary neutron star without splitting. Spin too quickly, and the core disrupts entirely, producing a different, more chaotic outcome instead. AT 2025 ULZ apparently originated from a progenitor star spinning within that narrow cooperative range. Scale here stretches far beyond ordinary stellar death. A single star's core, compressed within seconds, births two separate neutron stars simultaneously. Each resulting neutron star packs more mass than our entire sun into a sphere 20 kilometers wide. Two solar masses worth of ultra-dense matter, born together, merge again within mere hours of formation. Distant galaxies host this entire double detonation sequence roughly every few years, based on current estimates. Caltech astronomer Monsi Kosliwal recognized the pattern the instant the data crossed her screen. Kosliwal, working alongside Columbia astrophysicist Brian Metzger, had modeled this exact sequence over a decade earlier. Their theoretical papers predicted a massive star splitting its core into twin neutron stars during collapse. Reviewers at the time treated the scenario as an interesting but purely speculative possibility. Real astronomical data matching that speculation finally surfaced with AT 2025 ULZ in August 2025. Years of theoretical groundwork suddenly collided directly with genuine observational proof. Your instruments recorded contradiction. Their imagination recognized destiny. Persistent theoretical modeling gave Kosley-Wall and Metzger a framework other researchers simply lacked. Most observing teams treated the second brightening as contamination, noise, or a simple instrument error. Kosley-Wall's team instead recognized the pattern immediately, matching it against models built years earlier. That recognition transformed a confusing anomaly into confirmation of a decade-old theoretical prediction. Multi-messenger astronomy itself only became possible within the last decade. Gravitational wave detectors first confirmed a neutron-star merger back in 2017, opening this entire research field. Combining gravity wave data with traditional telescopes across the light spectrum created an entirely new observational method. AT2025-ULZ represents one of the clearest demonstrations yet of that combined method's full power. Detecting either signature alone, gravitational or optical, would have produced a far less complete picture. Peer review teams moved unusually fast once Kosley-Wall's team submitted their initial findings. Reviewers recognized the theoretical framework immediately, since Kosley-Wall and Metzger had published matching predictions years earlier. That existing groundwork accelerated the review process considerably, since reviewers already understood the proposed mechanism. Publication followed within weeks, an unusually fast turnaround for a claim this significant. Speed here reflects genuine scientific consensus forming quickly around solid, well-prepared evidence. Some astronomers outside the original research team requested independent verification using separate datasets. Independent teams reviewing publicly archived gravitational wave data confirmed the same underlying signal pattern. Verification like this matters enormously for a claim this unusual and historically unprecedented. Confidence in the double detonation interpretation grew steadily as more teams reviewed the same raw data. Confirmation like this reshapes existing models of how stellar deaths actually die. Textbooks currently separate stellar deaths into two clean, distinct categories without much overlap. Core collapse supernovas mark the death of single, massive, actively fusing stars. Neutron star mergers instead mark the much later death of ancient, already collapsed stellar remnants. AT2025-OULZ collapses that clean separation into a single, continuous double detonation sequence. One star's death now demonstrably produces both signatures back to back within hours. You feel the boundary between these two categories dissolve completely. Astronomers reviewing archived catalogs have already flagged several older events worth re-examining under this new framework. Some previously classified standard supernovae might actually hide a buried kilonova signature within their own light curves. Reanalysis efforts across major astronomical archives began within weeks of the AT2025-ULZ announcement. Every rediscovered case adds weight to the idea that double detonations happen more often than anyone previously assumed. Funding agencies responded quickly once the discovery's significance became clear to review panels. New observing proposals specifically targeting double detonation candidates received priority status almost immediately. Telescope time, historically scarce and heavily competed for, opened up for rapid response follow-up campaigns. Agencies recognized that catching the transition moment directly required near-immediate access once a merger candidate appeared. Infrastructure investments made today aim squarely at catching the next AT2025-ULZ within hours of its first signal. Your understanding of stellar death now carries a permanent asterisk attached. A dying star can apparently rewrite its own story mid-collapse, producing two separate endings. Each ending hides inside the other until careful observation peels back every layer. Confident classification built from the very first clear signal nearly buried this deeper truth completely. Patience revealed a sequence theoretical physicists had imagined more than a decade before proof arrived. Human persistence carried this discovery from speculative paper to confirmed cosmic event. Kasliwal and Metzger's decade-old models sat mostly unnoticed until reality finally caught up to their predictions. That gap between theory and confirmation represents years of continued observation, continued funding, and continued belief in an unproven idea. Scientific patience across that entire decade allowed two researchers to recognize destiny inside raw, contradictory data. Your next frontier already sits queued inside observatory schedules worldwide. Next-generation gravitational wave detectors, more sensitive than current instruments, prepare for deployment within the coming years. Wider sky surveys aim to catch double detonation candidates the moment their light curves begin misbehaving. Archived data from decades of past supernova observations awaits fresh review through this new theoretical lens. Every hidden signature still buried in old records represents a story waiting for someone patient enough to notice it. Every solved mystery inside this explosion reveals a deeper unknown waiting behind it. AT 2025 ULZ confirmed one specific double detonation pathway theorists proposed over a decade ago. Other pathways, still purely theoretical, may produce entirely different combinations of signatures nobody has recognized yet. The universe continues writing endings scientists have not yet learned to read correctly. Classification systems built today remain provisional, waiting for the next explosion to prove them incomplete once again.